Alright, hey guys, what's going on? So we're going to now talk about the completeness relationship in the context of quantum field theory. So what we've done so far is we've sort of put the completeness relationship within the context of just really what it is, right? What it is, how it works. And over the past 2 or 3 videos, we've done that, right? We've completely exposed ourselves to this relationship, how it's analogous to other domains of physics, or the mathematics of the physics. And what we want to do now is we want to use this to our advantage. Right? Last time we said that the completeness relationship helps us in determining a transverse direction to our to the propagation of our particles that are traveling in the z direction. So what we want to do here is we want to use this relationship now to generate a quantum field theory for this. So let's get right in. But before we get right into the video, make sure to hit that like and subscribe button. Now let's get into it. All right. So I'm going to erase this really quick. I'll talk about it in a bit. So what we want to do, or what we're doing here, is we're saying we've really defined this in the last video. This was our operator. It doesn't really matter exactly what the meaning is of these being up or down right now. We just want to think of this as an operator. So operating again on what we could call an arbitrary vector, right? But using A is sort of reminiscent of the fact that we're really interested in the electromagnetic field. The electromagnetic field is oscillating in different directions, but what we want to do is what we've done is we've defined a direction of propagation, and we've used that direction of propagation to our advantage. And we've said that what exactly is happening is we have I'll do it like this. Our field is propagating like so. That's not very good. Something like that. And at every point in space, say at this point in space right here, we have some value for our magnetic field and we have some value for our electric field. The electric field is traveling perpendicular to our motion, right? So here's our motion. It's traveling this way. And here is our propagation of our magnetic field, B, and the red is the propagation of our electric field, E. And we want to understand the propagation, or we want to understand the oscillations of these E and B vectors. The way to do that is to define the directions that are perpendicular to our motion. That is exactly what this guy did, this operator did. So that's why this completeness relationship is important. So what that looks like is right here. We've talked about this, right? And this guy right here again, so this guy right here is going to take our momentum forward vector and bring it to 0. So that means this is the relationship that we're looking at, right? This is the operator. These 2 vectors, you could call it arbitrary, but in this case we're looking specifically, we're interested specifically in the electromagnetic field case, and this is our direction of motion. This is going to help us define our direction of motion. These 2 vectors, when they're applied to this operator, will give us 0, essentially. Let's calculate now. Let's do some Heisenberg uncertainty principle stuff. This is our Heisenberg uncertainty principle. We want to see if this is going to equal 0. And it shouldn't, right? Because if it does, then that means we can understand the solution and its conjugate momentum at the exactly with a very high degree of accuracy. And that, again, is something we are trying to avoid if we're going quantum. So let's see exactly what this equals, now that we know what we know. So our conjugate momentum, again, was the derivative with respect to our solution. You can pause the video if you want to take this all in, but that's having this all fleshed out now. It looks like this. And then we do a product rule, again, right? This is a product of this and this. We're taking the derivative, right? So we want to take the derivative of A, and we want to take the derivative of the state. But we find out that this here is the same as this right here. All right? So we can cancel them out because they go to 0 because of this minus sign right here. Oop. So what we're left with is this guy, which is right here. Okay, we're getting somewhere. We then flesh this guy out to equal all of this. Right, so this is our most general solution. This is our completeness relationship, and this is a derivative. Right, so what we could do is we could say, well, here, this is a constant, right? So this is really all can be thought of as a constant. Okay? So what is this? Well, the derivative of all this with respect to A is going to be all of this, right? Because it's just multiplied by A itself, right? But only if what we want to do actually is that this was supposed to be I, right? Because we had an I right here. No, that was supposed to be J. We had our I was, where did the I show up? The I is right here. This is this I right here, right? Anyways. Well, not anyways, right? So we really want to keep track of our subscripts. But that's where that I comes from. And so this really only holds true, right? If I and J, or this is going to be the answer if I and J are equal, right? So what we do is we just make that a delta function, right? That's where these I and J's are going to show up. But we also I missed here, Y and X also have to be the same, right? Because this is the derivative of the solution with respect to, or the derivative with respect to the solution at a particular point Y. And this here was at X, right? So this guy here should have been at Y. And this is here at X. I'll make that a vector also. And here, I'll erase that and make that look nicer. Right, so this is only going to work out if our X and Y are equal. Okay, this has to be a Y also. But it also, like I said, has to only work out if our I and J's are equal. Right, so this X and Y, this I and J, we can mesh that all together. We can mesh all this together and define this as the transverse, right? So this is the thing that's going to do the transversing. This here, applied to this here, is going to be this X, Y, or this here is going to be our argument, X minus Y, and this is also going to be our argument. So I and J have to be the same, and X and Y have to be the same. Okay, we're compactifying this imaginary number also into this definition. But essentially, so this is what's called the transverse delta. So we're able to get the Heisenberg uncertainty relationship, right? Because if this equals the transverse delta, which it does, or this equals a delta function, that means that I and J, right? I and J must be the same, and X and Y must be the same. And if they're the same, then we get 0, right? Or we get 1, right? Remember, our argument for our delta function is if we have subscripts that, like I and J, if they're equal, then we get 1. If they're not equal, then we get 0. If we have arguments also for X and Y, again, x and y have to be the same for us to get 1, different for us to get 0. There's only 2 outputs to the delta, right? And what this transverse delta is doing, this transverse delta function is saying I and j must be the same, and x and y must be the same, and there's this transverse component which is given to us by this. Right, so we're able to uncover the Heisenberg-uncertainty relationship with the solution that is perpendicular to the form momentum. Right, so this is the solution that was perpendicular, and this is our conjugate momentum. So with this in mind, our method of going quantum is going to be as follows. So we had our Lagrangian. This is something we studied in depth back in chapter 4. We started with our Lagrangian, right? We then had our classical fields, so within our classical conjugate momentum, which is a derivative with respect to our solution. We applied that to Lagrangian. And then we said, okay, we apply this relationship, which is what we just derived, which came from this idea of getting transverse solutions with respect to, or perpendicular solutions. I keep on saying transverse, but perpendicular with respect to the motion or the direction of propagation of our particle. And with this solution, what we're going to be able to do now, or with this relationship, what we're going to be able to do now is get our creation annihilation operators, right? And so this is going to be the content of our next video, where we're going to derive these. We're going to have to use the completeness relationship. We're going to get something that looks a lot like a scalar field, because we didn't have the complexities of the spinors that we had to deal with. But this is going to be a video very similar to the Pauli exclusion video that we looked at before. We're really just going to go through a rote derivation of these relationships right here. And then after that, we're going to get into some really, really interesting, more quantum field-y related stuff. Right? We're going to have all of our fields. We're going to have our scalar fields. We're going to have our spinor fields. We're going to have our vector fields. My apologies again for the dog. And we're going to be able to play with all these fields and investigate them in full depth. And we're getting closer to the end of the book, which is exciting. But anyways, if you like this kind of content, make sure to hit that like and subscribe button, and I'll see you guys in the next one.